Welcome to Wireless Future. My name is Eric Larsson, and I'm here as always with my colleague Emil Björnsson. Hello, Emil. How are you today?
I'm great, as always. How are you?
I'm great as always too. That's good to know. So today is episode 34, isn't it, Emil?
It is.
It is, in fact. That's amazing. So I thought at some point we'd never make it to 10, but we made it to 34.
Yes, and today I think we will also sort of start referring back to some previous episodes as well, because we are going to cover things that we have mentioned before, but cover it in a different manner.
We might indeed. And, looking back, I think where we started the podcast, the very first episode that we recorded was on massive MIMO technology, which is a technology that both you and me have worked on for, well over 10 years by now. And it was also the technology that made it to 5G, right? I mean, there were lots of things that were discussed for 5G, extreme densification, small cells, new waveforms, and so forth. None of this really resulted in anything or made it. I mean, small cells have always been, are, and will always be limited by interference unless you make the cells cooperate phase coherently, which is essentially the cell-free massive MIMO or distributed massive MIMO concept. So now, looking at the future, still, we must ask the question, so what technologies are around the corner, right? And what are the driving applications going to be? And what performance targets are we setting up for the future? And in that respect, we'll also reconnect a little bit to, we did an episode, I think it was episode 10, like a year ago or so, on reaching the terabit per second goal. And that would be again the topic of the conversation today, because Emil, you attended in November 2022 a workshop at the Technical University Berlin with the theme how to achieve a terabit per second over wireless.
Yes, precisely.
So, how was the workshop?
It was a great experience. I was going there physically, and I think most of the speakers were there physically. There were good attendance also in the room, but also a lot of people attended online. So it was a great experience, and it was sort of this question that was asked in the title of the workshop that was open-ended on purpose, and people provided different types of answers and approaches to it and added different assumptions when providing their answers. So there were a nice variety of different thoughts around this topic.
So a terabit per second, that means, so tera is 12, right? So terabit means 1,000,000 megabit per second. Do we need at high bit rates?
That is certainly a good question. And one of the things that we are observing is that the data traffic is increasing all the time at an exponential pace. So from some kind of accumulated reason, the traffic will eventually grow to those numbers. And I think when it comes to optical fibers, we are trying to build those type of things right now. So to have wireless connectivity that can provide similar numbers, it makes sense that eventually we will be wanting to reach those numbers.
Yeah, maybe, but what are the applications? I mean, that would require such enormous transmission rates.
Right. So there are different reasons one can think about. One would be that we will use it to be extremely fast, but only for a very short period of time. So you sort of fill your cache in your device with a lot of information, everything that they expect you to watch on your TikTok or YouTube account in the next few hours, and then you don't need to be connected. You could also think about that it will be the collective traffic of many devices that should share this, or you just want to design your system for extreme scenarios And then knowing that due to the wireless propagation being complicated, I think the CTO from Huawei was there at the workshop and was sort of mentioning that as a rule of thumb, if you have a peak number, which would be 1 terabit per second, then 1/3 of that is what you could expect at the average, and maybe 1/5 of it or even lower is what you would get most of the time, perhaps, or you can expect it to be there. So maybe we also need to over-design in order to get something more reasonable most of the time.
Yeah, fair enough. I mean, but even a fifth of a terabit per second is quite a lot, right? So you're suggesting here that the use case would be that you just drive by an access point, and during the short time where you're in front of it, then you could quickly back up your entire hard drive or download in next month's of video consumption.
Right.
Or something like that. So there would be the use cases of these enormous bit rates.
Yes, and from an operator perspective, some of the challenges that they are facing is maybe that people are not actively communicating with extremely high bit rates but they're generating so much data, photos, videos, and stuff that needs to be transferred somewhere, either for storage in the cloud or just because there's a lot of people who are live streaming their lives and other people are watching. So there seems to be a big trend in a lot of countries that there's a lot of video streaming going on all the time.
Video streaming, yeah. So I mean, even already today, I thought in the networks, it's video streaming dominates the traffic, right? If you just count the raw bits. Yeah, and how about emerging augmented reality, virtual reality, extended reality, metaverse type of applications? Wouldn't they require also enormous terabit-ish rates?
Yeah,
where you are
exactly.
Connected with both uplink and downlink, I suppose. I mean, if you are wearing some smart helmet or glasses, then you might have camera or cameras even with high definition video that needs to go both directions with virtually no latency.
Yeah, this is certainly believed to be the next big device that will start accumulating a lot of traffic in the future. So if we saw 10 years ago when people started to use their mobile phone for everything, then the traffic was growing much faster than today. Now it's maybe 40% per year, but when these new things are arriving and start to be used, it might be increasing a lot. And I've been trying to look for numbers on what people are predicting that you would need for these type of devices. And as you were saying, it's both uplink and downlink, where uplink usually is complicated and might be the limiting factor. But some
why are you saying the uplink is complicated? I mean, is that because of some fundamental aspect of wireless propagation, or is it simply because you have less power typically available on the uplink?
Yeah, it's typically that you have less power. So if your device is topping up at 200 milliwatt or something, then the base station can use 10th of watt of power. And also I think regulations are also more for a user device, it's the total power irrespective of how much bandwidth you're using, while a base station can spread it out over bandwidth.
That's true. That's a good point. I mean, in most wireless networks, there is a fairly significant power imbalance between uplink and downlink, as I understand, right? I mean, you have a couple of 100 milliwatt on uplink and tens of, or even 100 watt on downlink, and even for macro cells today. Yeah. So
getting back to the numbers, by the way.
Back to the numbers.
Yes. So I think people are predicting everything from 200 megabits per second up to 1 or 10 gigabit per second. That is what you would need for some kind of 3D metaverse experience, of course, with very low latency as well. So I think even those predictions are not up there at 1 terabit per second. They're quite far away from it. But it's, if many people will use this at the same time, or if you want to guarantee that this is delivered everywhere, well, then you probably need to over-design things.
Right. I mean, there's still a gap. There are 3 orders of magnitude gap from a gigabit to terabit, right? So if a gigabit is sufficient for the metaverse, then well. But of course, it calls the question as to, now terabit, what does terabit per second mean? Is it like a terabit per second in aggregate when you multiplex many users together from an access point, or is it the rate per user?
Right. So
is there
I think that the most important thing is that the collective data traffic of all the users that are served by the same access point should reach 1 terabit per second, and that will happen much earlier. Then if you are connecting then this access point to the rest of the world, you will then have to send all of that collective traffic to the core network, and either you do that with an optical fiber, or if you want to have a wireless connection for that one as well, well, then you need a wireless connection with 1 terabit per second.
Right. Okay, sure. So, but a terabit could really refer to like the aggregate rate offered to many users multiplexed by the same access point.
Yeah.
Then, absolutely.
And I think this is also what we are facing today with 5G network, for example, depending on what type of network. I mean, most networks today are in the 3 GHz band, and maybe you reach up to 1 gigabit per second, but you typically don't need that as a user, so you divide it between the users that are sharing the network. And with millimeter wave, where there is technology not being deployed very much that can reach up to 5-10 gigabit per second, that's also not really meant for that a single user wants it all the time, but either you take turns or you at least on the average get a smaller fraction of it.
Indeed, but then I mean a terabit isn't so far-fetched in terms of requirements, right? I mean, if you think about 1,000 people standing somewhere like outdoors on a square or indoors, maybe some arena or stadium or something, and each of them wants to get this gigabit per second required to be in the metaverse, then 1,000 times a giga, that's a tera. So we're already there, right? So so what in terms of technology do we foresee and or need in order to reach this terabit goal? Is it like more antennas or more bandwidth or something else, or a combination perhaps of them?
It is probably a combination of these things. So the way to sort of easily picture how do you reach these big numbers is that, well, you have a certain amount of spectral bandwidth in hertz then, and you take that is the number of digital symbols you can transmit per second, and then each one of them you can encode a certain amount of information into depending on your signal strength, and that's what we call the spectral efficiency. And then you can transmit in parallel in different directions, different spatial ways, either to different users or in different directions, so that the receiving user also gets the signal from different directions. That I think we call typically beams, but it doesn't need to have a shape of a particular beam. So if you multiply these things like the bandwidth with the number of beams that you're sending simultaneously and how much information per symbol that you transmit per beam, well, then that multiplies up to your total bit rate.
Yeah, so what you're saying is like number of beams times the spectral efficiency per beam times the bandwidth, right? But isn't there a catch here? Like, I mean, the more bandwidth you use, the more power you need in order to combat noise, right? Because received noise or noise power at the receiver scales proportional to the bandwidth also. And the more beams that you transmit, the more power you need, because ultimately you need to split your total radiated power over the beams. So either you need, I thought here, also a lot more radiated power, or you need to sacrifice transmission range, or both.
Yes, so these are some of the issues. Then there are also solutions when it comes to having multiple antennas here, because at the receiver side you and at transmitter side you both get directivity from having many antennas, and you get the possibility of having directional transmission. So you can get at least some of these power losses from splitting the power between bandwidth and beams by just having more antennas that are collecting a bigger fraction, or that is directing the signal more accurately.
That is absolutely true. I mean, so effectively, with more antennas, we increase the aperture, which of course combats the link budget loss that we have to take inevitably if we or when we increase the bandwidth. So, what transmission ranges are we talking about here? I mean, because like for macrocellular coverage, then we're talking about like tens of miles, right, in coverage. For millimeter wave, it might be, I don't know, a couple of 100 meters perhaps. But for the terahertz links, how far would away from an access point could you stand with this metaverse equipment and get your gigabit simultaneously to all the other, almost 1,000, I think we said, users,
right,
who are also getting a gigabit? So what range would be like achievable here?
So that answer is really dependent on what is the spectral band that we are aiming for, because I think that is fundamentally what determines how the wave propagation will be behaving. And then, given that assumption, we can add antennas to different sides in order to try to improve things. But I think if we are building this in millimeter wave spectrum, well, then it will be limited to 100 meters or so. I mean, just as the system we have today, and it will reach further in line of sight scenarios, but it will be complicated to get the signal through multiple walls, for example. And if you build something at lower, like 3 gigahertz band as we're using 5G today, well, you will get similar kind of ranges as in those networks, which could be up to kilometers.
Yeah, clear. So returning to this argument that we need more beams, we need more bandwidth, and we need better spectral efficiency per beam, and ultimately at some point we might even need more radiated power. Then what numbers are we talking about here? I mean, what is the vision? How many antennas, how many beams, how much bandwidth, and so forth? Do you have any insight on that, Emil, or was there like any insight delivered at the Terabit workshop that you attended?
Right. So I think both myself and some of the other speakers were suggesting possible ways of reaching this number of 1 terabit per second, depending on what spectrum band you're aiming at. So, for example, there was one concrete example from Huawei which were saying that, well, let's go for millimeter wave, where you might be able to get 5 gigahertz of spectrum in this typical 30 to 70 gigahertz band, for example. And then if you try to then serve many devices, then in those bands you might be able to let each user device get 4 different beams. 2 with horizontal polarization, 2 with vertical polarization, and then coming from 2 directions each. Well, then you choose a modulation format, say 16 QAM, and each user will get like 40 gigabit per second, right? So that is certainly enough for the metaverse application we described before. And then you will need like 25 users to reach 1 terabit per second, and you can probably serve many more than that if you have the right kind of propagation environment.
So 40 gigabit per second per user, I mean, that would be with considerable margin sufficient for the metaverse application. And so let's repeat the numbers here. You said how much of bandwidth? You said 5
gigahertz.
5 gigahertz of bandwidth. You said 4 beams per user, and you said 2 bits per second on hertz spectral efficiency.
I said 4 bits per second on hertz.
4 bits.
So 16
4
QAM.
Bits, yes. Yeah, okay. So that makes 40 gigabit per second. And then multiplexing to 25 users at a time, that would make 4 this terabit. So, I mean, multiplexing to 25 users doesn't sound really so impressive, does it? I mean, even like in the early days of massive MIMO, I think folks envisioned like a race with 100 antennas, and then I think even you and me have a paper suggesting that the optimum number of, under some circumstances, optimum number of users to multiplex, wasn't it like 25 or 30 or something in that range? And I could also like envision much bigger multiplexing gains here, because ultimately, if you think about it at lower frequencies, or well, at any frequency, but particularly at lower frequencies, I mean, we have a fairly long coherence time, which means that we can squeeze in a lot of orthogonal pilots. So unless there's too much mobility in the environment, we could assign orthogonal pilot to thousands of users, which means that we could multiplex, we could learn, we could estimate a channel to thousands of users using the standard reciprocity-based, pilots and uplink, and then beamforming and uplink and downlink using reciprocity. And which means in turn, of course, that, you could make efficient use of thousands of antennas, right? In this book that came out earlier this year, on information theory for 5G and beyond, we had a chapter, and in that chapter is an example of, or really the question is how large a massive MIMO array could ever be useful. And I think we made a case there for an array with 40,000 antennas, multiplexing to 40,000 users.
Yeah.
So here the idea was that, okay, so a rather stationary environment at low frequencies. So we might have a 200 millisecond coherence time, 200 kilohertz coherence bandwidth. So that's 200 by 200 is 40,000, right? So you could squeeze in 40,000 orthogonal pilots, multiplex to 40,000 users, and therefore make efficient use of something like 40,000 antennas. And even at modest bandwidth, even with say 25 megahertz of bandwidth, even with modest spectral efficiency, bit per second and hertz, then we would reach this terabit in aggregate.
Yeah.
So I guess there are many ways to reach the goal, right? Either super large, massive MIMO arrays at low frequency bands, which of course will be of an appreciable size physically, but nothing really prevents them from being built.
No, exactly.
To going up in carrier and going up in bandwidth and using fewer beams or multiplexing fewer users.
Yeah, no, so actually so that example that I was mentioning with 25 beams, actually the example that was presented at the workshop was with 100 beams, so then they reached 4 terabits.
With 100 beams, okay. That is actually 4 terabits.
Yeah. No, and there were many other such examples also going down to lower frequencies, just as you did. I was presenting something for just the thing we use in 5G today. I think in Sweden the operators have a collective of 400 megahertz, and then I did some calculations there, what could be reasonable. Maybe you would need to send 500 beams in those scenarios to reach up to 1 terabit per second. And then, if you split that between, so every user get 2 or 4 beams, well, then you need a few hundred users as well.
Yeah, so is the overarching question here, do we need millimeter wave even to achieve the terabit per second goal, or would we rather just better stay with the lower frequencies?
No, I think we don't necessarily need it. And there were one interesting thing I picked up here, which I partially I've heard before, but also when it comes to new spectrum bands that will be of interest going forward. So often people are viewing that, we were using sub 6 gigahertz band in 4G, then 5G is all about millimeter wave, even if we don't know now that it's not. And then from that projection, we would go beyond 100 gigahertz to what the band people call sub terahertz in the future. Yeah. But one of the things that was mentioned was that there is this band between 10 and 15 gigahertz, which is in between what we use today and what millimeter wave technology is supporting, that could be of interest of using in the future. And there one might potentially find a sweet spot for this kind of things as well, where you have a little bit better coverage, but you also have smaller electronics. So there were an example of that you could build base stations of the same sizes of today, physical sizes, but with 4,000 antennas, and you can squeeze in 64 antenna elements in every user device, and in that way you can send a lot of beams per user as well.
So why is that? That this band has not been considered so much in the past, because
I'm not entirely sure. I heard people talking about this band from time to time, but I'm not sure why people give priority to the millimeter wave bands when we're going up in frequency and not to this band.
Yeah. So back to now all these beams and propagation, because to make use of so many beams, the channel will have to be rich enough, right? Or at least I could see that if you're in line of sight, then and you're multiplexing to many users. So beam here or stream means like one beam or stream or maybe a few per user. Then it'll be sufficient that these users are at different angles of departure from the array. And if the array is large enough that you're in the geometric near field of the array, of course you also get some depth resolution. So even if they're in the same like angle of departure, it would still work, right, the multiplexing. But if the object is to send multiple streams or beams to the same user, will the propagation channel support that? I mean, I can see that with a distributed MIMO array, the problem goes away, but with a like co-located array that is supposed to form all these beams, then won't we have a problem then?
Yes, that can certainly be a problem because you both need to have many possible ways that the signal can go between the base station and the user device, so that you could send beams in those directions, and then the directions need to be relatively well balanced in terms of signal strength, so that you actually benefit from dividing your power between them. And this is often one of the selling points of multi-user MIMO, that you easily get users with a few beams per user, and then you can get many beams because you have so many users. But when you are going up in frequency, if that is what we will be doing, going up to this 10, 15 gigahertz or a millimeter wave or so, then you also start to get this kind of you said the depth possibility in the radiative near field, and you also get the thing that the width of the beam starts to become so narrow that you might actually not be inside the main lobe of the beam through your entire device, and therefore you can send multiple streams to the device. But when I heard this example about 20 beams to one user device, I think that is rather far-fetched unless you really go up towards 100 gigahertz of carrier frequency or so.
Probably, yeah.
Or you're very close.
Yeah. So in terms of technology, what is the vision here? That we would go with fully digital beamforming or some sort of analog or hybrid technology? Or was there anything in the workshop here that hinted towards what the directions will be?
So this is an interesting question. I got the opportunity to ask people working in the industry about specifically this, and I got the answer that at least going up to this new band and 10-15 gigahertz, there you could easily extend today's technology and apply it there. So you could build this 4,000 antenna arrays and 64 on the user side with fully digital technology. Then I heard a claim that beyond that, you will need to look for other ways of building it, because today's CMOS technology is not efficient enough in terms of power efficiency, so that you will need to look for something else. So they weren't as certain about how you were going to build it.
Oh, you mean so once you reach above, you said 15
gigahertz, for example.
Gigahertz of carrier frequency. Oh, that's interesting. So there's like a cutoff point there, according to them, beyond which
with
fully
today's
digital
technology
isn't with today's technology. I remember some year ago we had a guest on the podcast from Beamwave, the Swedish startup building fully digital millimeter wave. I recall that we discussed, I think, higher carriers than 15 at the time. Or do you remember this, Emil?
Yeah, certainly. So they are aiming for building chips that can enable you to do digital beamforming also in the millimeter wave bands. And I guess the fact that it's a startup that works on this type of problem also illustrates that this is something where you really need to push beyond the state of the art.
Yes.
And their claims are that you can build this in ways that are as power efficient or inefficient for that matter as a hybrid beamforming or analog beamforming solution if you are building it in the right way. But apparently you need to build things in a smart way. And I think it also boils down to this question that we are using the antennas in this device for two different things. One is to get a beamforming gain or power gain to sort of overcome this issue that you need to divide the power between a lot of beams and bandwidth. And then we have the thing that you want to have the resolution of being able to receive and transmit multiple beams. And we certainly need a digital solution in order to send many beams and resolve them at the receiver. But there are possibilities of saving something in terms of the hardware design when you are only using some fraction of the antenna elements for getting a stronger signal, for example.
Mm-hmm. Yeah. No, I imagine there are a lot of tricks that could be used here, but anyways, the cutoff point, beyond which the fully digital isn't seen as feasible or power efficient enough, then there seems to be some controversy around that number. You cited the figure of 15 here, but others seem to think that it actually goes much higher up.
Yeah.
And I guess only the future can tell what will be feasible to build and how power efficient it will be.
Yeah, no, I think the point to make is that 15 is what you can reach today. If you just want to build a product, it seemed like...
with off-the-shelf available technology, got it.
Yeah, and then there will be more of an engineering effort and new innovations in order to reach beyond that.
Yes. So we talked a lot about multi-user multiplexing here now, and reaching a terabit per second in aggregate in a multi-user scenario. If we go back to point-to-point, would there ever be, to start with, a need to reach a terabit in a point-to-point application?
I think at least if you want to use wireless technology as a backhaul solution connecting a base station to the core network, well then as soon as the collective traffic in a cell reaches 1 terabit, you need this backhaul connection to have the same numbers. And I think what we have seen when it comes to millimeter wave spectrum was that it was used for backhaul links between base stations long time ago, and it's still being used. So if we will start to use even higher frequencies going beyond 100 gigahertz to what people call sub-terahertz and try to get a lot of spectrum there, then it will first happen, I think, for backhaul links as well.
Yeah, the backhaul is absolutely a compelling application. No question. So for the point-to-point.
But yeah, you would... I did some calculations as well. I think I talked about them in episode 10 as well. You could find maybe 50 gigahertz of unused spectrum in the sub-terahertz bands. And then you want to multiply with other things to reach up to 1,000, so you reach 1 terabit. And
the terabit,
yeah,
yes.
So if you have a line of sight between two base stations, you put up these things, well then you maybe you can get up to 1024 QAM, which is 10 bits per symbol. So then you have 50 times 10, you're up at 500. Okay, you need to send two signals at the same time to polarizations.
So there are many ways to multiply integers to get to 1,000, right?
Yeah, exactly. So I think it's certainly doable there as well, and I think that is the first use case for terabit per second in point-to-point settings.
Wow. Yeah. So one possible concern when speaking of this enormously high target of a terabit per second is energy or power consumption in the circuits. And not only the analog circuits, the actual RF and amplifiers and so forth, but also for the digital signal processing. Is that something that was discussed in the workshop, or any insights there that you brought home?
Yes, this was something that was certainly discussed from a number of different perspectives, focusing on some different components. So if you start with something I mentioned myself, then you were giving these examples with a very large number of antennas from one of your previous publications, and just doing some beamforming calculations, if you do the simplest kind of beamforming towards users without caring about interference, well, then the complexity of the computation you need to do is like number of antennas times number of users. So if you increase both of them, well, it scales very rapidly. And with more fancy things, it's like the number of antennas times number of users squared. That is the complexity. So complexity increases very rapidly for those type of things, for example. But there's also other components there that we can go through. And I think the starting point for this is really that we start to see saturation of what we can do in terms of circuit technology. So people are saying, well, Moore's law is dying out, so we can't squeeze in more transistors into a region, a certain area unit on our chips. And there have been something called a Dennard scaling in the past that has said that as the transistors get smaller, the power density stays constant, so computations automatically then becomes more power efficient. And this also seems to be a trend that has been going on for like the 1970s, but now it starts to die out. So this is a reason that we can't expect that just the sheer improvement in processor technology will come to rescue here and deal with everything. We need to really design our chips and our algorithms in the right way. Right, and one of the basic things might be the decoder, for example. So we need to have something that can take the received signals and then spit out 1,000 gigabits per second.
That's a lot, imagine.
Yeah.
1,000 gigabit per second. So how does that even relate to the clock frequency, I mean, on a chip, right? Because even on like an ordinary PC or, well, pretty much any digital circuit, you can't clock them much faster than a couple of gigahertz.
Right, exactly. So when I was growing up and started to follow computer technology in the 90s, then I remember seeing news articles about, the first computer reaching 1 gigahertz of clock frequency. And then we are still roughly stuck there. So I think if you buy a computer today, you get 1.5 gigahertz as your clock frequency. So this is one of the issues then, that for every clock cycle, if for simplicity say we have a 1 gigahertz clock frequency, then for every clock cycle you need to output 1,000 bits of information. And as input for those computations, you probably need more than that. So I got some examples of 4,000 bits of input information. That would be sort of the received signal plus different kinds of side informations about the signals that you need in your decoder. And just one operation will not do that. So in order to really be able to decode signals, then you will have to do some parallel computations and pipelining.
And not just some parallel. I think you need to do massively parallel processing, right? With thousands of bits at the same time in every clock cycle. So that'll require So there were some reports from a European project called EPIC that have been trying to build or design the circuits for both polar codes and LDPC codes, and I think possibly turbo codes as well, and trying to see which one would be most easily reach this kind of performance, and also do it with a limited amount of power. And I think what they noticed was that what they found most easiest to build was something for polar codes, where you need to still do a pipelining of like 60 clock cycles before an input results in output. So you need to have a lot of parallel computations there. And if you would do the same thing with an LDPC code, maybe you needed half of that number of clock cycles to output something from the input, but there were a lot of more, apparently the algorithms are such that you need to mix around the signal from different computations in different manners, and that made it much harder to build. Yeah, I guess with LDPC you need some version of belief propagation decoder that would shuffle around likelihood values.
Yeah.
Maybe that's like more demanding to implement.
Yeah, apparently. And their goal was to reach a power consumption of the decoder of 1 picojoule per bit. So what?
1 picojoule per bit. So now these numbers become at some point difficult to relate, right? Because, pico is like, let's see, giga is 10 to the 9, tera is 10 to the 12. Pico is 10 to the minus 12. Is
yes,
that
exactly.
correct?
So it's sort of the opposite of tera.
So the pico kills the tera somehow. So it's like a terabit per second times a picojoule per bit. That gives us a joule per second, which is 1 watt.
Exactly.
Of power consumption for the decode. So now we're speaking only of the decoding, was it polar or LDPC?
Yeah, I think this was polar code.
Yeah, and a watt that's appreciable. I mean, that's like on par with, or rather, I guess the transmit power, radiated transmit power is something like 200 milliwatt, right, for a like cellular cell phone or comparable device. So this is more, but
yeah.
It's comparable at least.
Yeah, and you typically don't get the specifications. I mean, if you buy a mobile phone, they are using a baseband chip often from Qualcomm, for example, and they don't say more than, oh, we are so power efficient, but what is the actual power consumption? People who are trying to do some measurements of this, connecting the device, different things, might be claiming that, well, today, maybe 2-3 watt is what the baseband chip is consuming. So this is not beyond that, but it will be a big fraction of the total power consumption. And you can imagine there's a lot of other computation that also needs to be done.
Yes, and I can also see that there are trade-offs here that need to be very carefully weighed. Like even with an LDPC code, I mean, you can trade performance versus decoding complexity, right? Just trading the degree distribution for, let's say, the threshold or a bit error rate. And at some point, it becomes incredibly expensive to gain the last few tenths of a dB in sensitivity. So... interesting. Wow.
But apparently they were able to build something that almost reached this target already, so that is at least a promising step. I think heat is still one of the issues because of this Dennard scaling means that you sort of the heat at this very small piece of silicon is very large, and I also heard this is one of the challenges now with millimeter wave devices that you can buy, that they get what the operators are claiming that you can get, but you only get it for a small period of times because then the device starts to overheat and need to downclock itself.
Yes. So do you think we'll eventually see like liquid water-cooled circuits for millimeter waves? So when you want to get this terabit and you turn on the water cooling of your chip, just like this gaming PC, some of them have water-cooled graphic cards, right?
Right, yes. Yeah, just as now we see, like, if you take Apple as an example, they have their regular devices, they have Pro and they have Extreme. Maybe we will have Extreme devices that are very... but possibly this is something you can do with some kind of augmented virtual reality device that you strap around your head, that there could be a lot of sort of... cooling from the air around it if you open up.
It'll all be weather dependent, right? When we have minus 10, 15, maybe even 20 centigrades, like sometimes for a few weeks in the winter in Sweden, that's when you can really turn on this Terabit, because then you can cool away the cool off the heat. Okay, great. So Emil, was there anything else in the workshop worth mentioning? I mean, for example, performance metrics. We've been now so far talking only about bits, really. I mean, a terabit per second, like raw data, presumably, but eventually these terabits will carry something like a video stream or, well, audio for that matter, sensor data perhaps, or information from some machine. I mean, could be updates from some machine, training some machine learning model, right? Or that sort of data. What are the performance metrics here that folks use and propose? Is it only raw bitrate, or is there something else that we ought to consider?
Yeah. So this is something that several of the speakers are also bringing up that took issues with the entire premise of that we want to reach terabit per second connectivity. So some people are saying, well, once we reach beyond a certain number, it doesn't really matter if we go up with another 10 or 100 times in speed, because what really matters for people is the timeliness of the data, that it is there when you need it to be there, and that you can get this real-time sense of things.
Yes. So when you say timeliness, do you mean latency or do you mean something else? Because I mean, I can, of course, on a superficial level, understand and agree that, well, if information is like outdated in like this augmented reality or metaverse context, then if you receive information about what somebody looked like or did or said like 10 seconds ago, then it's kind of useless, right? Probably. But is timeliness the same thing as latency, or is there a distinction there that could be easily explained?
Yeah, one can start to sort of split it up into some different aspects as well. So latency is one thing. I mean, just the freshness of the data. When was the data collected, and how quickly do I get access to it? But then you can talk about precision. So how well are you describing this data? If this is a high resolution measurement or low resolution measurement, and then how accurately did you actually? I mean, did you compress it a lot, or how accurately were the measurement as well? A very precise description of something that wasn't very accurately measured from the start might also be different, not so important. So one can play around with a lot of different types of aspects there too.
Yeah, and I could also see that, I mean, some types of traffic or different types of traffic require entirely different performance metrics, right? I mean, if you're backing up your hard drive, then you can't afford a single bit error. Your bit error rate has to be 0, or you could maybe afford that once in a billion times you back up your hard drive. I mean, you would get the bit error, but that bit error would be caught by some CRC check or some checksum or hash sum or something in the end, right? But on the contrary, if you're transmitting video, it doesn't matter so much. You might lose some frames and just interpolate, right, or just blank them out. And you're transmitting updates to a machine learning model. It's the same thing. I mean, you might need to train like one more round to converge, or it's not a big deal if you lose some data. So it seems to me that we would need here to define for each and every application specifically what performance means, both in terms of like error accuracy or error probability and transmission errors and so forth, and in terms of like delay or latency and freshness and timeliness and so on.
Yeah. And I think when people start to design new applications, for example, for the metaverse, you also have the opportunity of deciding how much data do you really need to transfer, and what data will you fill in with in your augmented reality, virtuality glasses. So I think the first metaverse, Facebook kind of things now, people don't have legs, because it's easier to transfer things in a good way if you just limit the amount of data. And you could, if people are in a virtual world, well, maybe you only need to send information that describes the human, and then you can create the world at different places as well.
Yes. Yeah. So you might just send like a high-level description, perhaps, and then use a gun or something that would just create a fictitious, like...
Yeah.
Okay, but then that seems to speak against the terabit per second to some extent, because then you wouldn't need as high bit rate, perhaps.
Yeah, so I think what typically is happening when it comes to applications is that programmers or people who build applications, on the one hand, they need to design something that works for the moment, but then they also like to not care too much about what connectivity that is required. So over time, it might increase a lot anyway. But on the other hand, people also might like the fact that you don't get an exact representation. I mean, on Zoom there are filters that is making you look a little bit more beautiful, and people might actually want to have that kind of thing. So you get
to apply them.
Yeah, so you want to send this kind of description of what you're doing, but also create a machine learning improved version of yourself that is visible in the metaverse.
Right. Right. Wow. So summing this up, Emil, what do you think? I mean, both what you brought back from the workshop and what you think in general is the most important or promising technology and research problem to work on in order to approach and reach the terabit per second goal? I mean, for example, one thing that we haven't discussed, I think, today at all is RIS, reflecting intelligent surface, and to what extent those could be a component here in the solution. We did talk about coding and MIMO, of course, and implementation and performance metrics and so forth. But what would be your summary in view of having, I mean, worked on these problems, obviously, but also attended this workshop? What are the most promising directions forward for folks like us working on academic research in wireless comms?
So I think that the reason to eventually reach 1 terabit per second somewhere will be in accumulated traffic over the area that a certain access point is delivering. And the problem there would really be to deliver this in a consistent manner so that you don't I mean, there were these simple descriptions. Oh, if you can reach a certain peak rate, well, then people at the edge of the cell get 1/5 of that. I think this is a bit of a exaggeration, because you will usually have a lot of coverage holes, and
yes.
If you want this augmented reality things to work really so people can walk around everywhere in the city, that will be one of the limiting factors. So,
yes. So you're really speaking to like uniformity of quality of service here, right? So there are some spots where you can get a terabit, but there are some holes where you get nothing. No, we need a solution where there might be some spots where you can get a terabit, but there must be no hole where you can get nothing, right? We must make sure you can everywhere get, I don't know, at least I don't know, gigabit or at least something, right? Yeah.
And I think the answers are not really to go up to sub-terahertz, where you will get even shorter ranges and more coverage holes, and you could potentially reach 1 terabit per second over point-to-point links, but why not dig fibers to our access point anyway? Probably we are already doing that. I mean, so I think it is more about being able to get good range from your base stations, good coverage, and then deliver something that reaches a few or maybe 10 gigabit per second most of the time to all the users. I think that is what you would like to have.
Yes, and handling mobility, right? I mean, if you stand still, then you might just as well connect the cables. So the real difficulty in wireless is always to handle mobility, I think.
Yeah, and you probably need different bands and the mix of different bands and their capabilities. So it's not one or the other of the things I described, but you try to use a good mix of that.
Yes, I mean, for example, there is this vision of a tandem architecture where you have a sub-10 gigahertz system operating through, well, some form of distributed MIMO eventually, providing macro coverage and ensuring this uniformity of the quality of service so that everybody gets like some minimum connectivity, whatever minimum means here, maybe even like a pretty high rate, in fact. And then on top of that, you might have sub-terahertz or millimeter wave systems that provide spot-wise extremely high bit rates. And then, of course, optimizing these components together and making that system in total delivering at optimum is an important challenge.
Yeah. And then certainly energy efficiency to actually be able to build this without spending a huge amount of power,
yes.
And to really making sure that this becomes more accessible, both in terms of coverage, and it's not only something for the inner cities, but that you can use this at many places. I think these are important things.
Covering the countryside with a terabit per second.
Yeah, or at least 10 gigabits per second in your house in the countryside.
Yeah. Absolutely, yeah. Great. Well, anything else, Emil, that you brought back from the workshop And
no, I think it's interesting to see there is a vibrant research now towards 6G. Maybe this is even further into the future that we'll reach these type of things. But I think people start to do real research now and present things, and not only visions about the future, but a lot of these things that were described was actually research that is ongoing or already have been finished in different projects. So I think that is promising towards the future.
I fully agree. That's really great to see. So with that, I think we might be closing up here, Emil. Thank you very much. That was a very educational conversation.
Thank you very much for the questions, and to the audience for staying with us.
To the audience, don't forget to like and subscribe us on YouTube.